Welcome to my talk. I thank the organizers of achems2021 for having given me this opportunity to present my research to you. The title of my talk is Machine Learning Ideations to Map Odorant Activity in Olfactory-Receptor Odorant Interactions. So I come from the Center for Biotechnology and Genomics at Texas Tech University. I want to thank the three people, Roshan, Neranjan, and Anuththara, who have, despite having full-time jobs, did all the heavy lifting as far as this project is concerned. Typically, when you run an experiment to functionally characterize an olfactory receptor, there is no rational, logical way to associate an odorant or a type or a group or a family of odorants or odors with a specific olfactory receptor. So it's a very expensive, time-consuming trial and error method. How does one arrive at a rational panel of odorants that are likely to bind, activate, or inhibit an olfactory receptor? What we have done is we started with 210 odorant molecules, and we used machine learning methodologies in order to identify the electronic structural features of each odorant. And the idea then is, can we cluster these odorants based on similarity of electronic and structural features? This way you can say that this group of odorants will likely bind, activate, or inhibit an olfactory receptor. So you always design potential pharmaceutical products that have a pharmacophoric feature, that's something that is efficacious, and to minimize the toxicophore aspect of that molecule, and that is the one that creates harmful side effects. Now, typically QSAR, quantitative structure activity relationship, is used at the National Center for Toxicology Research at the FDA in Arkansas. The scientists have developed something called as SDAR, spectroscopic data activity relationship. Conceptually, a lot of what we've done has been borrowed from the SDAR methodology. We've just been able to adapt, adopt, and kind of develop from scratch a lot of algorithms that we can apply. So if you identify a protein receptor for a drug for a particular disease, then there is one specific receptor, and then any kind of drug design is targeted towards addressing that single receptor, and the metrics are, does it activate or does it inhibit? Is it largely pharmacophoric? Is it largely toxicophoric? In the case of olfactory receptors, these belong to superfamilies, and so we have several hundred receptors for mammalian species which interact with, activate, and perceive several thousand odorant molecules. And of course, it's a promiscuous combinatorial relationship. Our approach is to basically explore the electronic structural features, which we think is a template for OR binding. We want to know each atom in the odorant and what is its chemical or electronic environment, and for that we study chemical shifts from nuclear magnetic resonance spectra. We've avoided hydrogens in this case, but we are focusing on the carbon-13 and nitrogen-15 NMR. Now, for the structural aspects, we want to make sure that we understand the positional parameters of each odorant and how they are related by distance, and are these then reproducible in a cluster of odorants. So what we do in our machine learning process is we create neural networks. Several neural networks are created. For example, there's a neural network which takes each odorant and ensures that the atoms are connected in a proper rational structure. The next neural network is composed of distance matrices of every atom with every other atom in the odorant, the interatomic distances, and the next two neural networks are associated with the chemical shifts. Now, before I go to the next step, I want to talk about the NMR, which Neranjan Perera developed. So he used the Gaussian suite of programs for quantum chemistry. We assessed the NMRs of each of these odorants using theoretical studies. So the first step in this process is you optimize the geometry, and then we determine the NMR chemical shifts. The next step is, of course, doing the processing, and Roshan Thilakarathne developed all the codes for this using certain deep learning artificial intelligence modules to process the information. We then took each of the compounds that we had and used a very traditional k-means clustering algorithm to be able to separate odorants into clusters. Now about the cohort. So the 210 molecules that we obtained were from the odor molecule database. And after the whole machine learning processing got taken place, we said, well, let's test out how many clusters we can create. Well, which cluster do we know has the best distribution? So we looked at all the parameters of the different clusters, and that sweet spot we got was the 15 cluster group. I just took one cluster at random, and let's begin to take a look at the odorants that make up this cluster along with the structure. Question that might arise is, why don't I just by inspection take compounds and put them in clusters based on what I think are the electronic and structural similarities. All right, so the different compounds that we have are allyl heptanoate, amyl hexanoate, and if you keep looking at these, you'll realize that there are some similarities. So right now, we could by inspection be able to create these clusters. Same with decanoic acid, octane dioic acid, and then the largest one in this group is undecanoic acid. Now what begins to happen is, let's look at the last two compounds. So we have the omega N methyl arginine. You still have that carboxylic acid group, and you have a whole bunch of carbon atoms in what is almost a straight chain. So you can see some similarities there. This one, of course, will catch you by surprise, and you might say, well, this is a potential outlier, yet our system put it into this. Certainly by inspection, you would probably take this odorant and put it into a category or a cluster composed of odorants that have ring systems in it. So what I'm going to share with you is the text file. So what you see here is a list of 43 distances that were reproducible exactly to the last decimal place, reproduced in every one of these, including geosim. But we just didn't rely purely on chemical shifts. So the electronic environment associated with that bond was exactly the same. The distance was exactly the same. And 42 structural electronic features in this case were reproduced. And what is a potential outlier? And the automatic choice would be geosim. All of our features were reproduced in every one of this odorant in this cohort. The real outlier in terms of the fewest structural electronic features was allyl heptanoate. So this is one of the reasons why this deep learning into electronic structural features that are not immediately obvious are necessary for this kind of study. In conclusion, what I would like to say is that we have now introduced a novel notion in the domain of olfactory receptor, borrowing at least the concepts from new techniques in drug design, and this will allow us to identify cohorts that will activate or inhibit olfactory receptors, allowing us to identify the rational panel that we talked about. But where do we go from here? We still have a couple of things that needed to be addressed. So when we cluster our odorants into these compounds, they all fall into individual clusters. How does this enable to address the combinatorial promiscuous nature? Now, we understand this odotope theory. There is an electronic structural feature in an odorant which is conducive to binding, activation, or inhibition with an olfactory receptor. We also have information from a classic paper by Linda Buck's group. And so how do we then use our methodologies in order to address the combinatorial aspect of it? Here's a new odorant selection protocol that we're developing, and we're still going with the 200 odorants. We will take those, and what we're going to do is, rather than take all 210 and feed it into the machine learning program, we're going to actually create label each odorant from 1 to 210, and then run a randomization process and create maybe 10 random groups where the odorants are distributed, maybe 50 odorants in random ways, will be fed into our machine learning methodology. In this way, then, what we can do is we can, for example, track each odorant and see in each process in how many clusters it finds itself in, and what are the electronic features that are contributing to that particular cluster. The title of this talk is a bit long-winded, but what I want to essentially call it is quantifying olfactory perception. And once again, thank you for the invitation to present my work.